오케이. 예, 이번 시간은 챕터 11 Atomic Mass Spectrometry에 대해서 다루도록 하겠습니다. 여러 가지 종류의 이제 원자 분광학들 중에서 이 매스 스펙트로스코피는 조금 차이가 나는데요. 우리가 기존에 봤던 업섭션이든 플로레센스든 이미션이든 이런 것들은 진짜 어떻게 보면은 진정한 분광학이라고 말씀드릴 수가 있겠죠. 그러니까 원자가 가지는 그 에너지 레벨, 바닥 상태랑 들뜬 상태의 그 에너지 차이에 의해서 생기는 그 에너지 차이를 측정하는 그런 것이죠. 여러 가지 방법을 통해서 흡수든 형광이든 방춘이든 이런 걸 통해서. 근데 아토믹 매스 같은 경우에는 말 그대로 매스입니다. 질량. 모든 원자는 다 제각각의 질량을 가지고 있죠. 그 원소들은 다 각각 여러분들 다 주기율표를 알겠지만 각 원자들마다 서로 다른 원자량을 가지고 있기 때문에 그 원자량을 측정을 하는 겁니다. 원자량을 측정함으로써 이 원자량이 이렇게 나오니까 이 물질 속에는 이 원자가 들어있고 이 원자 또는 이 원소가 들어있구나. 이런 거를 이제 알 수 있는 그런 방법이라고 할 수 있습니다. 그렇기 때문에 모든 원소는 질량을 다 가지고 있기 때문에 nearly all elements in the periodic table can be determined by mass spectrometry. 이 질량 분석법을 통해서 거의 모든 원소들이 다 측정 가능하다. 그리고 앞에서 우리가 배웠던 여러 가지 옵티컬한 방법들에 비해서 훨씬 선택성이나 민감도가 좋다. 훨씬 간단하고. 왜냐면 질량을 단순히 우리가 보는 것이기 때문에. 그리고 우리가 심지어 아이소톱, 동위원소라고 하죠. 동위원소들은 서로 다른 질량을 가지고 있기 때문에 그 동위원소들에 대한 정보 또한 우리가 알아낼 수 있다. 다만 단점은 비싸다라는 단점이 있다. 장비 자체가 조금 비싸고 인터피어런스 같은 것도 약간 더 심한 그런 경우가 생길 수 있다. 그런 정도가 단점이고 그 외에 굉장히 많은 장점을 가지고 있는 방법이 Atomic Mass Spectrometry입니다. 그러면 이제 이 질량 분석법이 원자 질량 분석법이 뭐가 다른지 기존의 다른 옵티컬한 방법들에 비해서 뭐가 다른지 한번 확인해 보도록 하겠습니다. Okay? So still a spectroscopy. So basically for optical method, we had this kind of general design of instrument, light source, slit, sample, wavelength selector, and detector, right? For mass spectrometer, similar, but for source we use ion. You remember from atomic emission, right? We need to use magnet and detector. Very simple, right? We simply measure ions using magnet. Okay? So let's see the detail. What is a mass spectrometer? Okay? It's very simple. Basically, we want to measure the mass of a certain atom or element. Okay? In previous chapter, you remember atomization process, right? During atomization process, if energy is enough or high enough to ionize that atoms, they can also generate ions, right? And those ions are positive ion, usually, in often case, just plus one ion. Okay? And that positive ions can be separated depending on mass, and we can detect it. Simply detect it. That's the general scheme of mass spectrometer. So for example, let's see a spectrometer, something like this. We have mass per charge, because most cases we have just positive one charge, so we can ignore this part. Mass, relative abundance. So mass is 16, 17, 18, 28, something like that. We can simply differentiate different mass, and also we can identify which species, which atom or element are present. Okay? Alright. So here shows the comparison between optical technique and mass spectroscopy. So comparison of optical ICP spectrum for 100 ppm cerium and mass ICP spectrum for 10 ppm cerium. Even with lower concentration, the spectrum is much simpler, right? Much easier to identify compared to optical signal, right? And as mentioned before, sensitivity of mass spectrometry is very good, right? Very small range of detection limit. Okay? Even below this microgram per liter is same as ppb, so even below, much lower than ppb range. Okay? Very good sensitivity. So let's talk about mass. Basically, mass spectrometry discriminate among the masses of isotope. Okay? So let's review some terms related to mass. Okay? Atomic mass of carbon is 12 AMU, atomic mass unit. So that's the reference point. Okay? We use this atomic mass of carbon, atomic number of 6, as 12. And compared to this mass of carbon, we designate other elements. So for example, chlorine 35.4527 AMU, for hydrogen 1.007494 AMU, something like that. Okay? The reference point is carbon. Okay? Alright. How about isotope? Okay? For carbon, we have 12 carbon, also 13 carbon. So for 12 carbon, the reference point is 12 AMU. For carbon 13, 13.3355. For chlorine, we have two different isotopes, chlorine 35, chlorine 37, with different mass. For hydrogen or deuterium, same, in the same way. Okay? Very simple, right? Each element, even isotopes, have specific atomic mass in units of AMU. Okay, just to review, just for clarification, atomic mass unit, Dalton, 1 atomic unit, blah blah blah. Okay, you can just check it by yourself. Alright. And there are several different types of mass, different ways to define and calculate mass of an atom, molecule, or ion. The first one, average mass. Okay. Average mass can be calculated using the atomic weight, which is the weighted average of an atomic masses of the different isotopes of each element in the molecule. Okay. So basically, we average all the isotopes. Okay. That's average mass. If there are different kinds of isotope and different abundance, we just average it. How about nominal mass? We only care about predominant isotope and round it to the nearest integer value. So we only care about predominant isotope for nominal mass. How about monoisotopic mass? Calculated using the exact mass of the most abundant isotope for each constituent element. Okay. So we use monoisotopic mass if possible in mass. Okay. Because we need to differentiate different isotope. Okay. Not averaging it or only selecting the predominant one. Okay, so let's see some examples. Alright, for C20H42, let's see. Sorry. ch20, H42. Nominal mass only care about predominant one, or carbon 12 and hydrogen number 1 with integer. So this is nominal mass 282 AMU. For monoisotopic one, okay, we use exact mass but only care about most abundant one, 12 carbon and hydrogen. For average mass, we use average number of carbon and hydrogen, considering the abundance of each isotope. Okay, so they have somewhat different number, pretty similar but somewhat different. Okay, so elements have various types of isotope. For hydrogen, hydrogen deuterium. For carbon, 12 carbon, 13 carbon, nitrogen, etc. Okay, they have different mass, different relative abundance. For example, for hydrogen, most of hydrogen is present as hydrogen number 1, similar for carbon, but for example, like chlorine, about like 1/3 is chlorine 37. Okay, different atoms have different atom or different elements have different abundance in each isotope. Okay. So if there is only one chlorine atom, 35 chlorine 35 and chlorine 37 should be present in this ratio 3:1. Okay. If there is only one bromine atom, bromine 79 and bromine 81 are present in 1:1 ratio, so they should be present as 1:1 ratio. If there are one chlorine and one bromine atom, things may complicated, right? So you have to care about the sum of each isotope of each element. Okay. Okay. So types of atomic mass spectrometer. Okay. So we learned about inductively coupled plasma, which generate really high temperature from like 6,000 to 10,000 Kelvin. So due to this high temperature, it can also generate many ions. Okay. There are also other ways to make ions. And we have specific instrument which is called mass analyzer, which is used to differentiate different mass. Okay, and usually we use this quadrupole mass analyzer. So we'll learn about the details about this quadrupole mass analyzer in the following section. Okay, atomic mass spectrometer. So we have ion source. So ionization occurring in this place using high temperature usually. And overall this tool is in very high vacuum. Very high vacuum, 10 to minus 5 to 10 to minus 8 torr, because we need to use high vacuum because we need to measure mass. If there is some other species that would disturb the measurement of mass, so we need really high vacuum, and we need mass analyzer to differentiate different mass of each ionic species, detector, etc. Okay. Here shows just the picture of the mass analyzer. So let me skip this part. Okay, so let's see how mass analyzer, especially quadrupole mass analyzer, works. So quadruple mass analyzer is very compact and relatively cheap one, and is very efficient to differentiate between different masses of species. So it consists of two pairs of rods, and each pair of rods are attached to positive and minus sides of DC source. So minus plus, right? Also, in addition to DC source, we also apply variable radio frequency AC source too. So both DC and AC potentials are applied to each pair of rods. Okay? Right? And ions which are generated in high temperature source, ICP, such as ICP, are accelerated into the space between rods in this direction, right? Between these rods here by small potential, 5 to 10 volt. Okay? And what happens is these AC and DC voltages are increased simultaneously while maintaining their ratio constant. So let's see the details in the next slide. And as a result, ions having a limited range of mass to charge ratio reach the detector. Okay? How can we select specific mass using this kind of tool? Let's see what happens. Let's first consider these two rods, which are positively engaged in positive potential, positive DC potential especially. Okay? Okay. Let's first consider the case of absence of DC potential. There's no DC potential, okay? Then we only engage AC potential, right? Positive, negative, positive, negative. For positive half of the AC cycle, okay, what would happen? Ions are positive ions, right? And if positive potentials are engaged in these two rods, ions would converge to the middle, to the center, right? Like A. Okay? If negative voltages are applied by this AC cycle, these ions would be diverged to the rods, right? Okay? Right? This is what happens when there is no DC potential. Okay? With this potential, what would happen? Okay? Heavier ions are less affected by AC, the converging and diverging, because it is heavy. Okay? Lighter ions are more deflected, right, during negative cycle, especially when they are diverging. Okay? Okay? So a pair of these two positive rods are a kind of high pass mass filter. Only filter out the high mass to charge ratio ions. Okay? Only heavier ions survive for these two positive rods, right? Okay? Let me see if you have a figure. Sorry. Something like this. Only ions with a certain mass above a certain limit survive for these two positively charged rods. Okay. On the other hand, a pair of negative rods. In the absence of AC potential, since they are negatively charged, all positive ions will tend to strike the rods, right? Because they tend to move towards the rods. Positive ions, negative rods, okay? With AC potential. Okay? For the lighter ions, this movement, this striking ions may be offset by the positive half cycle of AC potential, right? Okay? Okay? This positive AC potential will, like, what is it called? Offset some part of these negative rods. Okay. So a pair of negative rods operate as a low-pass mass filter. Only lighter ions have chance to survive going through between these rods, right? Okay. So only low mass ions could survive. So using these two mass filter, two pair of rods, only a certain range of mass, a certain ions with a range of specific mass will survive to the detector. Okay? Alright? So here shows some diagram, right? Between these two rods. Different mass to charge ratio, 900, 990, 1000, 1010, 1100, right? So red one, 1000, survive, but this one, 990, strikes the rod. Same for 1100, okay? Something like that. So only specific ions with specific mass survive to the detector, right? Here shows the high mass filter, low mass filter. Alright. So here shows a typical mass spectrum. So you can clearly see the difference between different ions, right? Different number of mass, 12, 14, 16, 23, something like that. Very specific. Okay? There are also other types of mass analyzer other than quadrupole, such as time of flight mass analyzer, double focusing analyzer. So you can check the details in the textbook. Okay? How good is this? We already have learned that mass spectrometry is very sensitive compared to other optical techniques, right? So we can, the dynamic range is really large, right? Very straight standard curve, okay? Even 4 orders of magnitude. Nearly all the elements can be measured by this mass spectrometry. So it's very good for qualitative as well as quantitative analysis. So ISP-MS is very handy, very useful tool. There are some spectral interference. For example, isobaric overlap. So some elements, some isotopes have same mass. For example, 40 argon plus ion and 40 calcium plus ion have same mass of 40. So if there are these two elements present together, they might overlap. Okay? Also, similarly, polyatomic ones could have same mass, 56, 56, something like that. But that's not that common. Okay? Spar interference. Okay. Also, refractory oxide can be formed. basically they cannot. Actually, this one is for this one. So, at high temperature, refractory oxide can be formed, which prevents the exact measurement of mass. Also, they could differently charge the ions, but they have same mass, right? Positive 1, 2, 3, something like that. So, that could be just an example of spectral interference that we can encounter in atomic mass spectrometry. Okay.